Greetings to the respected faculty. I am Lasya Mandapati from CSC AI&ML B section. My roll number is 24951A6686, and today we will be discussing one of the fundamental and foundational topics of probability theory, sample space and events of a random experiment. Probability is not just abstract mathematics, it underlies real world processes, from weather forecasting to financial risk, from machine learning to everyday decisions like predicting traffic. And the building blocks of probability are the concepts of random experiments, sample space, and events. In this tech talk, we'll define these terms clearly, explore different types of sample spaces and events, and also connect them to practical application. By the end, you see how these basic ideas form the foundation of all advanced probability and statistics. Probability is a study of uncertainty. It provides a mathematical way to describe and analyze situations where the outcome is not certain. Every probability experiment begins with three key components. First, the random experiment, which is any process that produces an outcome we cannot predict with certainty, such as tossing a coin or rolling a dice. Second is a sample space, the set of all possible outcomes of that experiment. For example, the sample space of a coin toss is heads and tails, while for a dice roll it is 1, 2, 3, 4, 5, and 6. Third is the concept of events, which are specific outcomes or sets of outcomes within the sample space. For instance, rolling an even number when throwing a dice is an event. These three elements, random experiment, sample space, and events, form the foundation for all of probability theory. From them, we develop methods to calculate probabilities and apply them to real world problems. So, what is a random experiment? A random experiment is any process that can be repeated under identical conditions and whose outcome is uncertain. Think about tossing a coin. The process is well defined. Flip a coin once. The possible outcomes are heads or tails. But before you actually toss, you cannot predict whether it will land on heads or tails. The same is true for rolling a die, drawing a card, or measuring rainfall in a day. In each case, you know the possible results, but you cannot guarantee which one will occur. And finally, we also know that this concept of random experiment theory is at the heart of probability theory. Now, let's examine the key features of a random experiment more closely. Uncertainty. The outcome cannot be predicted with certainty before the experiment is performed. Well-defined outcomes. Even though uncertain, the outcomes are precise and unambiguous. Repeatability. The experiment can be repeated under identical conditions. Assignability of probabilities. We can meaningfully assign probabilities to each outcome. Take tossing a coin, for example. We cannot know in advance if we will get heads or heads tails or tails heads or tail, but the outcomes are clearly defined and can be assigned probabilities. By contrast, something like the time of sunrise is predictable and therefore not considered a random experiment. Once we have a random experiment, we can define its sample space. The sample space S is a set of all possible outcomes of the experiment. Each possible outcome is called a sample point. For example, when tossing a coin, the sample space is heads and tails, as you can see here. And when you're rolling a die, it's simply 1, 2, 3, 4, 5, and 6. Notice how the sample space captures every possible result of the experiment. It can be finite, like coin tosses, or infinite, like measuring the exact time until the bus arrives. Sample spaces can take on different forms. So, Let us categorize them. Finite sample space. They have a limited number of outcomes. For example, rolling a die. There are a total of 6 outcomes. Infinite sample space. They contain infinitely many outcomes. For example, uh, the time until a bus arrives could be any non-negative number. Discrete sample space. Here, the outcomes are countable, even if they are infinite. Example, the number of customers arriving in a shop. Continuous sample space. Outcomes form a continuum, meaning that they take values in a continuous interval. For example, the exact height of a person or the exact rainfall in a day. This distinction matters because different probability models apply depending on whether the sample space is finite, discrete, or continuous. Now, let's move on to events. An event is simply a subset of a sample space. In other words, it is a collection of outcomes that share some property. For example, in rolling a die, the sample space is 1, 2, 3, 4, 5, 6. An event might be getting an even number, which is 2, 4, and 6. As you can see, 2, 4, and 6 is a subset of the sample space that satisfies the condition that it is an even number. And in tossing 2 coins, an event could be getting 2 heads, which is hedge, which is also a subset of the sample space. Events are central to probability because we usually assign probabilities not to single outcomes but to these subsets. Events themselves can be classified into several types. Simple events. These contain only one outcome. For example, rolling a 4, only 4. Compound event contains more than one outcome. For example, rolling an even number. You can roll a 2, 4, or a 6. Sure event, the entire sample space. For example, when rolling the die, the event of getting a number between 1 and 6 is certain. Impossible event, the empty set, meaning no outcome satisfies the condition. You can take an example of rolling a 7 on a die. By categorizing events, we can apply probability rules more systematically. Two important concepts are mutually exclusive events and exhaustive events. Mutually exclusive events. Two events are mutually exclusive if they cannot occur together. For example, when rolling a die, the event rolling a 2 and the event rolling a 5 cannot happen on the same roll. Exhaustive events. A set of events is exhaustive if taken together, they cover the entire sample space. For example, if you take a coin toss, the events head and tail are exhaustive events because one of them must occur. Together, mutually exclusive and exhaustive events partition the sample space, dividing it into non-overlapping paths that cover everything. For every event, there is a complementary event. If event E occurs, then its complementary E dash is the event that E does not occur. Formally, E dash is equal to S minus E, meaning all outcomes in a sample space except E. For example, rolling a die. Let E be the event that the number rolled is even. Then E dash or its complement will be the probability that the number rolled is odd, which is simply 1, 3, and 5. Another important property is that the probability of E plus the probability of E complement is equal to 1. In other words, either the event happens or it doesn't. Complements are very useful in calculations because sometimes it's easier to find the probability of not happening and subtract it from 1. Now, we come to the difference between independent and dependent events. Independent events. The occurrence of one does not affect the probability of the other. For example, tossing two different coins. The result of one coin has no influence on the other. In cases like this, probability of A intersection B is the product of the probability of A and B. Dependent events. The occurrence of one changes the probability of others. For example, drawing two cards without replacement. If the first card is an ace, the chances of drawing another ace decreases because one ace has already been removed. Its formula is given as P of probability of A intersection B is equal to probability of A times probability of B by A. The difference is crucial. Independence means no influence. Dependence means probabilities shift. You can think of independent events as happening in separate worlds, whereas dependent events are connected by cause and effect. These concepts are not just academic, they show up all the time in daily living. For example, weather forecasts. Rain or no rain is an event in the sample space of possible weather. Traffic. The number of cars passing a checkpoint in 1 hour is a random variable based on the sample space. Customer arrivals in a store or calls to a call center. Games or lotteries. Every draw or spin is a random experiment with defined sample space and events. By thinking in terms of random experiments and sample spaces, we can make sense of these uncertain outcomes and manage the risks. The applications also extend into many fields. For example, in science and engineering, reliable testing of systems predicting failure and possibilities. In computer science, they are used in randomized algorithms, simulations, and machine learning models. In finance, it's used for stock price movements and insurance risk models. In the medical field, they are used for clinical trials where patient outcomes are uncertain but modeled probabilistically. This is why mastering these basics is so important. They're not just theoretical but essential for modern applications. To summarize, a random experiment is a process with uncertain but well defined outcomes. The sample space is a set of all possible outcomes. An event is any subset of that sample space. Events can be simple, compound, mutually exclusive, exhaustive, complementary, independent, or dependent. These concepts are the building blocks for all of probability theory and its applications. If you understand these fundamentals, you are ready to move into deeper probability topics like conditional probability, random variables, and distributions. Thank you for your attention. I hope this lecture has given you a clear picture of random experiments, sample spaces, and events. These simple but powerful ideas form the foundation for everything that comes later in probability and statistics.